Hi everyone, we are back and we are going to talk about today rubber elasticity. Hopefully you've come across polymers in a previous course. You definitely have, hopefully, and then hopefully you've taken my Mech 202 course. And if not, there's about 150 videos you could kind of watch. But we've talked about, or actually hopefully you've experienced that polymers, and we'll actually examine the mechanical properties of polymers as when we get into linear viscoelasticity. But polymers can behave essentially under different temperature, strain rate conditions as an elastic solid or a viscous liquid. So there's some characteristic relaxation time, tau star, where if we pull faster than tau, faster than that relaxation time, we're going to behave like an elastic solid. If we apply slower, then we'll behave like a viscous fluid. Now, polymers also have some other very unique properties in that they can, some of this behavior, actually this time scale behavior, polymers can behave like elastomers. And these elastomers can basically give rise to this kind of rubber elasticity. So we're going to describe essentially what are elastomers, how it looks, and what are the kind of stress strain responses of a rubber elastic material, and specifically how we can calculate what is the Young's modulus for an elastomer or something that behaves basically for rubber elasticity, this kind of general concept. And again, all of these properties that we're going to talk about in terms of polymers hold for a wide variety of soft materials. So polymers, polymers, proteins, et cetera, et cetera, et cetera. So when we're thinking about rubber elasticity, we're going to think about the mechanics of rubber, and this basically a network. So when we think about a rubber, typically, or polymer, we think of this kind of spaghetti. But oftentimes you'll run into polymers, and those kind of occasionally those spaghetti chains will kind of entangle. And they cannot, basically move past one another. So instead, you can envision some, rubber networks or elastomers specifically as this kind of network of crosslinks, and they could be chemical or physical. So you can have crosslinks that are chemical. So there could be like a disulfide bond. That's probably the most famous for rubber, essentially vulcanization of change. But it can also be physical entanglement. So you could have basically a glassy regime or glassy structure of a block of polymer that basically it acts like a physical or actually a chemical crosslink. So even though it's a physical crosslink, it's basically stuck forever. Like they are permanently, this chain cannot move independently. So they're just basically fixed lattice points, essentially. Like this chain cannot move independently from this chain at this particular point. So they're basically fixed and stuck. So when I pull this material, this region is going to kind of move collectively. So this region in between here, it could kind of wiggle and move around. So there could be different relaxation timescales, but these will kind of move all collectively as points. So that's kind of the idea here. So basically, the entire rubber is connected. Individual chains are not capable of diffusing completely independently in response to perturbation. So we are going to, when we get into, and actually in this derivation, we're going to make a series of assumptions. But the key thing is when you're looking at a rubber, we're still looking at very flexible chains that can easily rearrange. But the presence of the crosslinks in between prevents the chains from completely flowing. So you get the origin of rubber elasticity comes from the presence of these crosslinks, either chemical or physical. So you get some solid-like mechanical behavior as a result of that, because again, they can't just flow past one another. So there are different relaxation timescales. So there's a long one that's characteristic of the entire solid. That's the entire solid that's cross-linked. So this whole network. There's also shorter timescales. Again, basically in between the cross-links. So diffusing polymer chains in here. But in this framework, we're going to make this following assumptions. So in between our permanent crosslinks, our chains are going to behave Gaussian. So basically, the distribution of their sizes is kind of just Gaussianly distributed. So if I look at the end-to-end distance squared of my chain, the probability, they're Gaussian. So that's just kind of one. Our temperature is well above TG. That's great, because we know that before, because again, this is the distinction. All of our other rubber, if our temperature is well below TG, we could use our other theory to describe the elasticity of this material. Flexible chains, again, they could rearrange, move. Chain deformation occurs by conformational changes. Again, so there's no, so you're basically pulling apart. The polymer looks like this, and then when you stretch it, it goes to this. No relaxation by chain slip. Again, the network is fixed on the time scale of the experiment. So we're not pulling slow enough that they could essentially, if we pulled super slow, they would eventually, especially if they're physical crosslinks, the chains could slip past one another. So they are not able to slide past one another. So we're assuming that we're able to pull such that this network is behaving like a solid. A fine deformation, again, microscopic deformation occurs by the same amount as macroscopic deformation. So the chain dimensions can be described as the ratio of the chain, the microscopic deformation can be basically described as the same as the ratio for the dimensions of the overall network. We'll see how that actually occurs in just a second. No crystallization of the chains. So again, as we stretch, we're not going to assume, like in that kind of necking and drawing, that there's going to be some recrystallization event. So no crystallization. And then this is the key one. No change in volume. We are incompressible. So we cannot, basically, our volume is not changing in this system. So our volume is constant. So this entire framework is going to allow us to describe two different systems. So mechanically deforming a gel or a rubber elastomer, and then gel swelling. So oftentimes when you deal with a polymer network, if I have this kind of cross-link network and I have I mix with a good solvent, those chains want to interact with the solvent and they swell up. But if that polymer or that elastomer is hydrophobic, and you put it in water, it's a bad solvent and it's going to kind of collapse in on itself. So this same framework can describe these two very, very, very different processes. And the key thing that we kind of are going to be working with, and the kind of assumed knowledge that we're going to work with, is that when I stretch the chains, or when those chains change, conformations, stretching your polymer is going to decrease the conformational entropy of the chain. So we had this, or hopefully you've seen this before in other courses, but our free energy of stretching is going to essentially come from our entropy term. And we see here, this is just temperature. This is the deformed size of our polymer. This is the initial size. As we stretch that polymer, as we make it grow, so here we're looking only at stretching. There's another description for compression as well. Same idea holds. As I stretch my polymer, my Gibbs free energy increases. That's not good. So as I stretch my polymer, I decrease the conformational entropy of my chain, and my free energy increases. So we need to kind of see, and essentially, that is going to be the energy component that basically tries to restore, so opposes pulling. So as I pull on material, my free energy increases, my conformational entropy decreases, and thus I'm going to have this entropic spring-like restoring force that opposes pulling, and that is going to be the origin of the elasticity. So we'll describe our rubber elasticity system next, and then we'll get into a fun derivation. Okay, thanks.